A warm welcome to today's Dassault Systèmes eSeminar on co-simulation for efficient battery management. This webinar is part of our electric vehicle eSeminar series. My name is Michael Werner and I'm a SIMULIA portfolio introduction specialist and leading you through today's eSeminar. Today we have two presenters, Euriel MALPIECE and Thorsten GERKE. Euriel MALPIECE is SIMULIA Business Development Executive. Euriel joined Dassault Systèmes in 2017 and is part of the SIMULIA organization. He has 10 years of experience in the engineering software area and is responsible for innovative projects linked to numerical simulation with a strong focus on the automotive industry. He's based in Stuttgart in Germany, and prior to moving to Germany, he studied physics and economics in France. Our second presenter, Thorsten GERKE, is a senior solution consultant for CATIA Systems Solutions. Thorsten holds a Master of Science in Mechatronics Engineering and an MBA in General Management from FOM Business School in Munich. He has 18 years of professional experience in simulation-based systems engineering for physical and embedded systems for automotive applications. He started his professional experience at Bosch Automotive in model-based systems engineering for automotive cranking motor systems in 2000. Subsequently, he moved into software industry and held various positions, including applications engineering, pre-sales, technical marketing, product marketing, business development, for example at Avanti, Synopsys and MathWorks. With 40 plus international publications on automotive applications in leading automotive magazines, I'm glad we have you both on board to present this eSeminar. A warm welcome to Euriel and Thorsten. The stage is yours.
Many thanks, Michael. Many thanks for the very nice introduction. So before we start, I think that it is good for you, maybe for those of you who don't know Dassault Systèmes, maybe to have a couple of words about our company. So it's going to be 2 slides. After this, I'm going to present you our vision of the electric vehicle of the battery market. And then after this, we will have a deep dive into our technical solution, CATIA systems and SIMULIA. So let's start with our presentation of Dassault Systèmes. So we have about 15,000 passionate people across the globe that are the heart of the company and a large R&D team connecting across 56 laboratories delivering simultaneously combined software for our 3D experience solutions. Dassault Systèmes has the largest PLM market share with more than 200,000 customers in 12 industries worldwide. A fundamental aspect of 3DS is partnering with clients who are leaders in their own industry segment, typically leaders in innovation and on the cutting edge of technology in order to answer tomorrow's market needs. Our ecosystem of 12,600 selected partners increased our collective knowledge in the areas of sales and services, software development, education, and social development. Over 200 companies develop software complementary to our own. And last but not least, the composition of our shareholders has been consistent since our introduction on the stock market. The majority of the company is owned by the Dassault family and the company's management. This stability enables a consistent long-term strategy and long-term investment, enabling to be one step ahead of the competition. Now let's have a look at the solutions we can offer, the different solutions we have. On the left side you can see our compass for our 3D experience platform. At the bottom of the 3D experience compass, our virtual plus real solutions, bringing the virtual and real world together. Delmia for digital manufacturing, 3D Varia for the realization of real-time consumer experiences, and SIMULIA for the numerical simulation on the physical level. On the left side, our 3D modeling tools like SolidWorks and CATIA, but also BioVia for chemical, materials and bioscience research, and GeoVia for geologic modeling and mining engineering. At the top of the compass, you will find our social and collaborative solutions with 3D Excite for high-end 3D visualization in real time, and Innovia, which is our product lifecycle management solution. And last but not least, on the right side, our information intelligence tool, Exalit for data analytics and NetVibes for dashboarding and business intelligence. And what you can see on the right side is that the 12 industries where we are present. And today, because we are going to talk about battery development, so our solutions are especially thought for the transportation mobility industry, for the high-tech industry, and the energy process and utilities industry. So we have identified at Dassault System four megatrends where we are present, where we have solutions. The first one is electric, connected, and autonomous vehicles. The second one is new customer experiences. The third one is quality, cost, and regulation. And the last one is mass production to mass customization. And today, because it's about battery engineering, it's a lot about electric vehicles, so we are going to be focused on the first of the megatrends. At Dassault System, for each of our solutions, we try to have an approach based on the corporate initiative which drive our customers. In this case, for the development of innovative powertrain solutions, we have identified with our customers 6 main key business drivers which cover all the possible engineering analysis of our customers or our customers want to realize. Increase safety, increase drive performance, reduce cost, reduce emission, reduce weight, and increase drive comfort. And regardless the kind of powertrain, ICEs, fuel cells, or electric, they are always the same. It's always the same key business drivers. And what is changing for each kind of powertrain are the defined objectives to address those business drivers. For example, in the context of the electrification, maximize energy density with high energy density electrode materials for increased drive performance, improve NVH behavior of electric vehicles for increased drive comfort, and reduce electromagnetic radiations for increased safety. And this approach is quite good because it allows us to offer our engineering solution in the form of different workflows and analysis addressing directly the needs of our customer. Our approach is a kind of tailor-made. So I wanted to give you an overview maybe for the key business driver, increased safety, about the different workflows we have defined for this. So for example, battery system engineering, the thermal behavior modeling in 1D. And we are going to talk about this. For battery cells, the structural integrity. For battery cells, again, the thermoelectrical losses in 1D and 3D. Battery cells, the thermal runaway studies, and so on. So for each of the key business drivers, we have defined very high-end workflows that are ready to use for our customers. So now at this point, the question is, why do our customers need, now even more than ever, to use best-in-class digital technologies to create the next generation of electric vehicles? And the answer is quite obvious when you have a look at this slide. Of course, we still see on a regular basis new exciting innovation in the ICE area. So for example, the Mazda compression ignition gasoline engine, or the new Bosch diesel technology. But the ICE powertrain is a mature technology, and the usual player, OEMs and suppliers, are perfectly established since decades on the market. There is perhaps less need for a revolutionary way of designing such powertrain systems. And on the other hand, the electric vehicle technology is pretty young, and there is still a lot of place for technical improvement. And we are facing some sort of race between established players and newcomers to offer as quick as possible electric vehicles, which will be as efficient as diesel petrol vehicles. And this time pressure and this need for short-term engineering excellence, coupled with the different points you can see in this slide, mean that our customers have to completely rethink the way they engine electric vehicles. And in this context, the use of the numerical simulation and of virtual twin of the powertrain system are becoming absolutely critical. And that's where we, Dassault System, wants to play a big role in partnering with you and offering the right tool for the electric vehicle application you can have. And this slide is an overview of the different vehicle components of our customers. Our customers will have to rethink and redesign in order to develop best-in-class electric vehicles. These are basically the technological challenges our customers face. So let's start, for example, with the HVAC system, because of course it's critical to optimize it in order to ensure that the cabin vehicle thermal behavior will be ideal. And we know that the operating conditions of an EV are different from the operating condition of an ICE vehicle. And it's something we definitely have to take into account. And reducing the energy consumption of the HVAC system is also becoming pretty critical to preserve the battery charge. The second point we can talk about is a chassis, which will be probably redesigned in order to fit the requirements of an electric powertrain. Due to a lower center of gravity in the vehicle dynamics has to be analyzed again. And for this, we have the right solution, for example, with SIMPAC. And one important question is, at this point, can I create chassis concept which I will be able to use for different kind of powertrain? We know that modularization of such components is currently extremely important for our customers. And other important components impacted by the powertrain electrification are listed on this slide. So for example, the vehicle architecture, the body, the power electronic systems, the electric drive, and of course the battery. And today, our focus will be on the battery. I wanted to give you an overview about the business processes we have defined for this. So you can see the different area we have. So for example, electric powertrain system engineering, power electronics, electric drive engineering, full vehicle integration, and battery engineering. So battery engineering is in green because we are going to talk about this, but you can see that we have different business processes for all the kind of analysis you want to have on an electric vehicle. And here are the workflows for the batteries, which we have defined with our customers and with our colleagues. So what you can see, for example, at the top of the slide, materials development. So it's about battery material design, and we have the right solution for BioVia with that, for simulation, for chemical simulation, for molecular modeling, and so on. Workflows like electrode properties and intercalation, electrolyte characterization, solid electrolyte interface characterization, and so on. And of course, the goal is to consider the whole as a system, and to use the analysis you can have on the material side for further analysis, for example, on the system design side, on the 3D design side, and performance analysis. That's the different areas you can see. On the system design area, you can see the different workflow we have, and we're going to talk about this. So for example, electrical behavior modeling, mechanical behavior modeling, thermal behavior modeling, energy behavior modeling, and system analysis, and everything in 1D. On the battery cell engineering, and there we are in 3D, we have different workflows too that are ready to be used at our customers. So for example, physical design definition, electrical chemical performance, thermoelectrical losses, thermal management, and so on. And we have the same when we speak about the module and the pack with electrical mechanical design, strength and stiffness, safety, durability, thermal management, and so on. And with that, now we're going to go into the deep dive, the technical deep dive. So Thorsten, if you would like to start with the 1D, with the system engineering presentation, it would be a pleasure to pass over to you.
Yes, can you also give the presentation rights to me? Okay. Okay, very good. So in the remaining part of the presentation, we want to talk a bit more in detail as to how we solve the challenges on the battery development using the as-defined industry workflows, and taking a glance at the complete picture of the model-based battery development process solution provided by DS. It can be seen as a two-dimensional process. So two-dimensional means that you have on one side the process along the complete supply chain, starting from the development of the material, subsequently turning that into battery cell technology, developing the needed battery modules, which are then assembled into a complete battery pack and system, and finally integrating that into a complete entire vehicle system architecture. So meaning the whole process going from materials up to the battery system and vehicle level technology. The other dimension relates to the level of abstraction of the simulation model, so meaning 1D or 3D model, which depends on the development stage, but also the needs of your particular use case scenario. And the whole solution is made up by 3 brands, including CATIA, SIMULIA, and BioVia. Of course, the foundation for a solid battery system are the materials of the battery in terms of electrodes, electrolytes, and so forth. The model-based development of the materials is something that can be done using our BioVia solutions. Even though it is not the focus of the session today, it is important to understand that simulated results from the material and chemical simulation can be very beneficial inputs for subsequent steps in the model-based process to characterize models that are described on a higher level of abstraction. So let's start to talk first about the systems engineering activities to develop a battery. It is certainly a valid question, why do I need a 1D simulation if I could also simulate everything in 3D? Well, a major reason for the need of a 1D simulation is the simulation performance. It runs much quicker than a 3D simulation. In some of these battery simulations, for instance, aging analysis require to analyze time frames of a couple of years to predict the battery behavior in operation. And with Daimler as the 1D simulation solution of CATIA, we have capabilities in place to describe all aspects of the single battery cell relevant to analyze the performance as well as aggregating that subsequently to a complete battery system with a very scalable modeling approach. And the scalability in Daimler is facilitated through the fact that we use the Modelica modeling language as the foundation for our technology to enable finally a flexible modeling and simulation approach. And this is very beneficial when you want to run, for instance, a design of experiment by varying the number of cells in a battery module, thus the whole battery pack, in order to quickly analyze the impact on the overall battery performance. This is something that can be done very easily and very scalable in Daimler. In addition, for the cell module as well as battery pack development, it is often beneficial to have a connection between the 1D and 3D modeling worlds. So this is meant in two regards. For instance, to leverage results from a 3D simulation in order to characterize a 1D model in Daimler, or to directly co-simulate a 1D and 3D model. Of course, the needed and preferred approach depends on the particular needs of your use case. So meaning the key takeaway here is this solution that we are talking about today supports the coupling of 1D and 3D models in a bidirectional manner. So when we talk about the prediction of the battery behavior using model-based design, then we have to take into account several different domains. And the core function of the battery is at the end of the day to supply electrical power to the overall vehicle system. Therefore, an accurate description of the electrical behavior of the cell is key to predict this. However, the electrical behavior also depends on the temperature, for instance, and lithium-ion batteries can only operate within a restricted temperature range, so otherwise they can even get destroyed, which means the battery also requires a thermal management. Therefore, the thermal behavior is another important domain that needs to be taken into account here. The electrical as well as the thermal behavior also impact the aging behavior. And aging in the context of a battery means the decreasing capability over time to store energy, so meaning a decrease of the capacity over time, as well as an increasing electrical losses during charging and discharging cycles, so meaning an increase of the inner resistance of the battery over time. And finally, the battery is assembled also into a mechanical pack that, for instance, undergoes mechanical deformations, which needs to be taken into account too. And DS technology for battery system engineering enables to integrate all of these different domains into a model-based framework from the cell up to a battery system or even the use in vehicle system level simulation. So we're going to take a closer look at two of these workflows for electrical and system analysis. Okay, so let's start with the electrical workflow first. Daimler, as the CATIA system solution for 1D battery system simulation, provides a special library for battery modeling, so that facilitates battery developers to describe battery cells and packs in a very flexible and scalable fashion. Using the electrical model in Daimler, we can analyze charging as well as discharging cycles, and the electrical model delivers, for instance, information about the electrical losses that are dissipated into heat. And we can also compute the state of charge through it. So in simplified terms, how much energy is still in the battery. For these two types of models are actually provided in the library. An electrochemical model that is based on the Newman-Doyle-Fuller model, which is quite popular for this type of analysis. And the model can be parameterized with material data. So the model is very suitable if it requires to take very detailed effects into account, so it computes the lithium-ion concentration and the resulting electrical potentials in the battery. However, this model is preferably useful for short-term analysis as it is computationally pretty resource-intensive. The other second type of model that is available in Daimler's battery modeling library is an electric circle level model that is computationally fast and especially powerful when complete modules and packs need to be simulated. perhaps also in conjunction with a battery management system. And unlike the electrochemical model, this model needs measurements or simulated battery data that comes, for instance, from a prior 3D FEM simulation, for instance, from our SIMULIA products, to characterize the model. And we have automated solutions available in order to carry out that process. So we're going to see in a subsequent step that this model also embeds capabilities to consider, for instance, also thermal and aging behavior of the battery cell. Okay, so let's take a look at the second workflow, the system analysis workflow for batteries as an example. This now brings together all of the different domains that we mentioned previously, meaning electrical, thermal, mechanical, and aging behavior, and provides a high-fidelity battery simulation solution. So starting from the electrical model in Daimler and characterizing it, in a subsequent step, that model gets equipped with thermal behavior. So we have two options to get the thermal behavior into that model. So either leveraging a pure 1D thermal simulation in Daimler, where the model gets characterized through measurements or data from a prior 3D FEM simulation, for instance, our SIMULIA products, or we can directly also co-simulate Daimler's electrical model with a 3D thermal model from our SIMULIA products. So an analysis like that facilitates, for instance, to identify thermal hotspots in the battery, which is important to be taken into account for thermal management, but also from a safety point of view. Another important step is to add the aging capabilities to the overall simulation workflow. And Daimler's battery library covers aging behavior. So the model supports a calendaric and cyclic aging, as well as allowing to integrate aging models from external sources. So for instance, from suppliers such as cell manufacturers. So assembling these models now together to a complete battery pack, either the pure 1D model or as a coupled simulation of 1D and 3D models, this system analysis workflow allows the user to simulate a complete battery system, analyze and understand the performance of the battery, and finally validate it against the requirements to further optimize the behavior according to the specific system needs. Okay, so let's take a look at a quick demo for the system analysis workflow. In this particular use case, we want to optimize a vehicle battery system in terms of vehicle driving range and battery charging time. In order to do so, we've put together a model for an electric vehicle that is associated with a couple of requirements relating to battery requirements as well as requirements for the vehicle. So meaning, for instance, for the battery, the number of cells, and for instance, for the car, as a requirement, for instance, the maximum allowable weight. So let's go down to the CAD model of the overall system. Overall, we have 10 modules in our battery pack. And in order to validate the performance of our system, we have defined so-called advisory checks. Underneath these advisory checks are finally, at the end of the day, simulations that are being carried out, and we verify the results of our simulation against our requirements. So we could see here, for instance, 3 requirements that are being verified. One is the driving range, and the other 2 criteria is the battery charging time as well as the battery weight. We can see 2 of our requirements are being satisfied. However, there's one requirement, the driving range, which is at the moment not being satisfied. So it means we have to do some optimization of our vehicle and battery design. In order to do so, we go back to our requirements. What we do is that we adjust the requirement on the module. So meaning we change the size of the module, we change the module width, and what happens in the background automatically in the platform is that the number of cells is being changed and the whole CAD is actually being adjusted. So now we have to also again go back to the simulation in order to verify whether our system now really from a performance perspective meets our requirements. In order to do so, we have actually implemented a couple of simulation models in Daimler. One model, for instance, in order to simulate the driving range behavior, another one in order to simulate the charging time behavior. First of all, we go to the driving range simulation, open the model in Daimler, and in order to simulate a drive cycle, we need to select a particular drive cycle. In this case, we take the NEDC cycle. Once we have made our selection on the driving cycle, we can launch and kick off the simulation. So once the simulation has succeeded, we can analyze and review simulation results. And for instance, you can see in the lower right corner the state of charge of the battery, and we see that at the end of the driving cycle, we end up with around about 13% SOC of our battery pack. Okay, so that was the first simulation in terms of looking at the driving range behavior after we have made a change in our requirements. Let's take a look at the charging time behavior. For that, we go again to the other simulation model in Daimler. That's the architecture. Quite simple, a battery model that is being connected to a charging system. And go into the model, portrays a bit the architecture of that. This is, for instance, a snapshot of the model of the battery cell, including the thermal part of the model, including the electrical behavior of the model, as well as covering the aging part of the battery cell behavior. So again, launching the simulation in order to simulate the charging behavior, we can subsequently review and analyze again simulation results. If we look at the signal in the middle of these three simulated signals, we see that we end up at around about 95% SOC once the charging process has completed. So now we have carried out the required simulations for driving range, and in order to analyze the charging time, we now update also our life cycle data in order to perform again our advisory checks to double check the performance against the requirements. We can see we have now an improvement here. The driving range as a requirement is now being satisfied with this design update. The battery charging time is also still satisfied. However, now the battery weight, and overall it means also the vehicle weight, is no longer going to be satisfied in terms of a requirement. It comes due to the fact that we have increased the size of the battery module and thus also increased the weight of the battery module. In order to further optimize, it will require now the engineer to take some further measures in order to improve the performance, in order to finally really address all the requirements. All right, and with this little demo, I'm at the end of the system engineering part, and I would like to hand over again to my colleague Euriel.
Thank you, Thorsten. So now that we have seen which capabilities we can offer for system engineering, we'll talk a bit more about, we'll talk a bit more in detail about 3D simulation with Dassault System Solution. So the goal is to realize analysis. The goal is to realize analysis which are as near as possible to the reality and to be able to precisely characterize physical effects everywhere in the geometries. So for this purpose, we will use different Dassault system technologies which are completely integrated, like the FE solver of Abacus, implicit and explicit, like our CFD capabilities, Navier-Stokes-based technologies, lattice Boltzmann method with Xflow and Exa, like FESAFE, for example, for fatigue and life cycle analysis, etc. And those 3D simulations will be even better if they are coupled with 1D system analysis to take into account dynamic effects coming from the electrical or the thermal system. And today, our focus will be on the cells and module packs for the numerical simulation, but we could also have presented our workflows for the integration of the battery system in the vehicle, for example. So let's have a look at our solution for the 3D simulation battery cell engineering. So on the right side, you can see the different workflows we offer. For example, electrical behavior modeling, thermal behavior modeling, mechanical behavior modeling, aging behavior modeling, and system analysis. And on the next slide, we will have a deeper look at the safety topic. Unfortunately, we won't have the time today to talk about the others, but those workflows are well defined, and it would be a pleasure to discuss them with you if some of them could be interesting for you and for your company. On the left side, what you can see is you will find a kind of summary of the business value of this approach. It should enable you to better understand the chemical, electrical, mechanical, and thermal effects in the cell, and so perhaps to reduce the usage of costly materials, to predict aging and degradation of the cells and improve their life and capacity, and to better understand the impact of abusive events like collision, intrusion, overcharging, and so on. So the first step is to use a CAD model coming from Dassault Systèmes. So when we have a look at the safety workflow, to use CAD model coming from Dassault Systèmes tools like CATIA or SolidWorks, or coming from a third-party CAD. We also feed the system with information about material properties and possibly physical test data, and we can start with the first analysis. Because we could start, for example, with structural analysis relative to mechanical abuse events like excessive loads, unwished large deformation, and predefined scenarios like a crash or nail intrusions. Effects on the casing like plastic deformation or even fracture could also be taken into account and applied to the cells. Second step, based on what happens on the mechanical side, we will be able to directly use the output of such analysis to move forward with a short circuit study. Will cell components get in contact and generate a short circuit? Do I face steering problem with the separator? Do I risk an electrolyte leaking? Will the mechanical abuse cause a short circuit and a thermal runaway process to begin? Those are the questions we would like to answer with step 2. And step 3 deals with the thermoelectrical abuse and different factors which are listed there. Overcharge, so for example, problem at the cathode, oxygen release and pressure buildup and so on. But also over discharge, external short circuit overheating and so on. And these factors could act as the kind of catalyst of a beginning thermal runaway process, and it brings us to the next step, the last point, or the last point, the step 4. With the analysis of the thermal runaway process itself with generalized short circuit, exothermic chemical reaction, structural collapse, and so on. And the goal is really to understand there how it happens and how is the propagation in the different cells and in the system. So it was our workflow for safety on the battery cell engineering. Now I'm going to talk about 2 workflows for module and packs we've defined. The first one, it's about, we have different workflows for this. So we suggest the same approach for battery module and pack engineering with 5 workflows, which you can see on the screen: electromechanical physical design, thermoelectrical management, strength and stiffness and durability, safety workflows, and reduced order modeling for thermal, electrical, mechanical, and aging. And I will briefly present 2 of them, so thermoelectrical management and safety. What is the business value of this approach? So the business value is to identify the best heating and cooling strategies to guarantee optimized operation temperatures, analyze thermal and mechanical strategies, for example, thermal expansion, plastic strain, susceptibility to cracking, fracture, defects, and so on, and in order to ensure that the system won't fail and will last over a large number of sales cycles. And of course, the last point is to better understand and reduce the impact of abusive events like a collision. So our thermal management workflow for the battery pack engineering starts with the input of the available data, so CAD data for the module and pack, characterized material properties, and the experimental cell test data if they are available. We will first calculate the heat losses in the system using the electrical behavior coming from Daimler and computing energy losses in each cell via 1D or 3D modeling techniques. We will also assess losses in bus bars and in the equivalent circuit models and apply them in the 3D models to obtain temperature distribution information in the system depending on the operating conditions. With the second step, we will begin to take into account the cooling system. In the first instance, we will run the analysis in a steady state modus and then let computed fluid flows and thermal fields interact with each other. Step 3 will offer the possibility to run transient analysis for short periods with co-simulation using the lattice Boltzmann method for computing the fluid flows and the EFI method for the thermal simulation in the solids. We will extract the heat transfer coefficients and use them for further thermal analysis in the solids, and we'll have the possibility to include, of course, environmental condition as binary condition for even more precise simulation analysis. And the last step will allow us, with the help of our best-in-class post-processing solutions, to assess the results, share them with colleagues, and generate linear and time-variant radius order model to use for further analysis on the vehicle level. Then now I come to the last workflow I wanted to present today. So the safety workflow for battery pack engineering in this case. So in this case, I don't want to go too much into details because it's similar to the safety analysis I presented for the cells engineering. We're going to start with mechanical abuse analysis. It's going to be the first step, so simulation of abusive loads and large deformation with crash, and intrusion scenarios, for example, and characterization of what happens on the structural integrity of the cells. Then, second reason for thermal runaway process is to start, we will have a look at the thermoelectrical abuse simulation with external short circuit overheating, cells swelling, overcharging and discharging, and etc. After that, assuming that a thermal runaway happens, analysis will be conducted with input coming from the cells. For example, heat propagation and thermal runaway propagation velocity on the module and pack components. We'll try to answer the question, what are the heat channel and which influence are the runaway processes on the solids and material for the module and packs. And finally, once we have characterized the thermal runaway processes, we'll be able, with the help of parameter studies and design of exploration analysis, to assess a lot of different design scenarios in order to reduce drastically the safety risk we could have. So that was the workflows I wanted to show you. It was about the numerical simulation in 3D. As you have seen in the presentation, we have a lot of different workflows. It was just 3 of them. Maybe I think we have time for questions. If you have questions, it will be a pleasure for us to answer them. I don't know, Michael, if we already have some questions we could answer right now about the different processes, what we have shown right now in our presentation.
Yes, all right. Thank you for your presentation, guys. For everyone again, please ask your questions in the GoToWebinar chat or Q&A window. And while we're waiting for more questions, I already see some. Let's have a look on the upcoming slides just to make everyone aware before we get into the Q&A session. On the next slide, so just some organizational details again. There will be an email announcing the availability of the recording afterwards, so you can have a second look or even share it with your colleagues. And I also want to announce that we have, of course, newsletters and social media out there, so feel free to join us there to don't miss our upcoming eSeminars. And we had one eSeminar last week on electromagnetic simulation for tomorrow's vehicles. So there we have the replay already available. If you're interested in that, have a look. And otherwise, if you can't find it, come back to us. So let's get into the questions. First question I've seen so far is, which solver is used for the CFD simulation in 3D simulation?
So it's a very good question. We have 2 possibilities because we have 2 kind of technologies. We have the Navier-Stokes based technology, and we have different projects. Some of our customers are using this kind of technology for such analysis, and we have the lattice-Boltzmann technology with two solutions, X-Flow and Exa Power Flow, and we also have different projects with that. So depending on what you want to do, what you want exactly to do, so we have the 2 possibilities, and we have experiences with both solutions.
Sounds good. Next question is, what is the source of material models of the cells or battery modules for 3D mechanical and thermal simulations?
So we have two possibilities in this case. So of course you have the possibility to make the chemical characterization of the cells directly with our solutions with BioVia, for example. And in this case, if you are a user of BioVia, or if you want to use it, or if you have colleagues using BioVia, for example, in the material research, you can take the information coming from BioVia, it's integrated, and you can use them for further analysis. It's possible. And what is also possible is that you create your own libraries. So I mean that what we want to do, we want to offer you a kind of open platform where you can feed the whole system with the data you can have for this. So of course it's possible to make some measurement or to get the information from suppliers and to put them in our database, for example.
All right. I think that's a question for Thorsten. So the question is, what exactly is the Daimler battery library? Can you elaborate on this?
So the battery Daimler is a collection of a couple of different elements. The key thing for that is the models for the battery cells, and as already previously shown in the demonstration, the cells are built up on 3 different modules. One is the coverage of the electrical behavior, the other one relates to the thermal behavior, and the third element covers the aging behavior. You do not necessarily need to take all of these elements into account when you simulate a battery cell or when you aggregate it later on to a module or battery pack. You can activate and deactivate some of these things, but the cells are actually finally the key element for that. In addition, the battery library also contains already battery packs that are part of that library solution, as well as there is also, along with that, solutions available for battery management systems. So you have some templates for that available.
Another very general question is, which is the next technology used in battery after lithium-ion battery?
I think it's an improved lithium-ion battery. That's what we hear out of discussions with all of our customers. Lithium-ion is currently really state-of-the-art, and it will be improved over time.
I think so we are working on that too. So if you could have some projects on that, so for example a research project, so we are interesting. So we already have some discussions, we already have some experiences. So for example with solid state batteries. So I guess it should play an even bigger role in the future, and we are developing our solutions for this too.
Perfect. Are there any more questions? One I do see is related to the demo, I think. There was selected the new European driving cycle. Is this already predefined in the system, or do you have to specify that on your own?
We have already a predefined set of driving cycles that can be selected directly in Daimler, but you can also add your own custom cycles if you want. If there is a cycle, for instance, not available, you can add it yourself.
That sounds great. All right. Do we have any more questions? I think we give it 10 more seconds, and if there's nothing popping up anymore.
And if you have more questions, so you can see our contact details on the screen. So it will be a pleasure to have a discussion with you about this. So on the SIMULIA part, on the simulation part, on the 1D system engineering part, so it will be a real pleasure. And if you could be interesting to get more information about our solution BioVia for chemical characterization, so we can also organize a discussion with our colleagues who are specialists in this area.
All right. At that point, thanks again for your great presentation, Euriel and Thorsten. And I think if there are no further questions, we're ready to close the call. All right. Thank you, guys.
Thank you very much.
Thank you.